Hello guys, welcome back to my channel Gamma Digamma. So in this video I would like to implement a result that we derived in the last video. So if you haven't seen the last video, please do that before watching this. And as always, let's get started. Okay, so it might seem ages, but after ages we're actually calculating an infinite series S that's defined as sum from n equals 1 to infinity of Riemann Zeta of 2n plus 1 divided by 4 to the n times 2n plus 1. So if you want to write out some terms of this guy, that will be Riemann Zeta of 3 over 4 times 3 plus zeta of 5 divided by, it will be 4 squared, which is 16 times 5, plus Riemann Zeta of 7, 64 times 7, and so on, going to infinity. Okay, so if you've watched the last video, you might remember what I'd said in that. If we have an infinite series which has a Riemann zeta associated with it, we can, or rather we should, use the expansion of Digamma, the Taylor expansion of the Digamma function. So that's minus Euler-Mascheroni plus sum from n equals 1 to infinity of x to the n minus 1 to the n plus 1 Riemann zeta of n plus 1. Now the problem here is that if you want to write out some terms, this is going to be zeta of 2 times x minus zeta of 3 times x squared, and zeta of 4 x cubed, and so on basically. Now the challenge here, the problem here is that here we had odd arguments for the Riemann zeta. Here we have all arguments from 2 to infinity. Okay, so let's just keep this as it is. Now look at Digamma of 1 minus x. I'm just changing x to negative x. So when I do that, I have sum from n equals 1 to infinity of minus x to the n minus 1 to the n plus 1 zeta of n plus 1, and when I expand this out a little bit, I have zeta of 2x minus zeta of 3x squared minus zeta of 4x cubed, and so on till infinity. So now if we want to get rid of the even terms, the terms which have an even argument for the Riemann zeta, we need to add these guys. So if we have Digamma of 1 plus x added with Digamma of 1 minus x, we'll just get the Euler-Mascheroni's will add up. This guy cancels with this, so we basically have negative 2 times Riemann zeta of 3x squared, and then this 4 cancels out, so I'll just write the next term after it, 2 times zeta of 5 x to the 4th, and so on. So to generalize this, we have 2 times sum from k equals 1 to infinity of Riemann zeta of 2k plus 1 multiplied with x to the 2k. Okay, fair enough. So comparing this with our original problem, I mean, if we change, say, k to n, again it's a variable, we can change that. We have this, we have s, right? I mean, if we change x to a half, we'll have this 4 to the n factor also. But the challenge is this 2n plus 1 in the denominator. How can we generate a 2n plus 1 over here? How can we do that? Well, what if we integrate? So if we say integrate from 0 to t, negative 2 Euler-Mascheroni minus 2 times sum from n equals 1 to infinity, zeta of 2n plus 1 x to the 2n dx. And I would have to do that on this side as well. Fair enough. Okay, so I will get negative 2 Euler-Mascheroni times x minus 2 times sum from n equals 1 to infinity, zeta of 2n plus 1 x to the 2n plus 1 divided by 2n plus 1. So you see, now we got the factor. That's why this integration step was necessary, but this is still evaluated from 0 to t. Okay, so this becomes minus 2 times Euler-Mascheroni times t minus 2 times sum from n equals 1 to infinity, zeta of 2n plus 1 t to the 2n plus 1 divided by 2n plus 1. Okay, and this is still equal to integral from 0 to t digamma of x plus 1 plus digamma of 1 minus x and a dx. Okay, now I want to take t to be 1/2 because I want this 4 to the n factor over here, right? Okay, so when I do that, I have negative 2 Euler-Mascheroni divided by 2 minus 2 times sum from n equals 1 to infinity, zeta of 2n plus 1. Here we'll have 2 to the 2n plus 1 can be multiplied with like a separate 2 out there, and a 2n plus 1 factor being equal to integral from 0 to half now because of this substitution, digamma of 1 plus x plus digamma of 1 minus x with a dx in here. Okay, so now the 2 and the 2 cancel out. Same thing with this guy over here. And finally we are left with negative Euler-Mascheroni minus sum from n equals 1 to infinity, zeta of 2n plus 1 divided by 2 to the 2, which is a 4 to the n, and 2n plus 1 factor like that, is equal to, now I would like to use the definition of the digamma in the sense that the digamma is the derivative of the natural log of gamma of whatever argument we had. In this case is 1 over x minus, for this guy, natural log of gamma of 1 minus x. I took the negative because the x has a coefficient of minus 1, so I have to obey chain rule and take a negative so that it becomes plus later on after differentiation. Now we have minus Euler-Mascheroni minus, now this guy is just the original s that we started with, and that's equal to, we have to take the antiderivative of a derivative, and by the fundamental theorem of calculus that's just the function itself. Now the natural log of gamma of 1 plus x minus natural log of gamma of 1 minus x, evaluated from 0 to half. Okay, so when that happens, we have negative Euler-Mascheroni minus S is equal to natural log of gamma of 3 by 2 minus natural log of gamma of half minus natural log of gamma of 1 minus natural log of gamma of 1. So these guys cancel out to 0. Here we have minus Euler-Mascheroni minus S is equal to natural log of gamma of 3 over 2 divided by gamma of 1 half. This is just using log properties, and now I can use the recurrence relation of the gamma function to be 1 half times gamma of 1 half in place of gamma of 3 over 2 and gamma of 1 half. So these guys cancel off. Minus Euler-Mascheroni minus S is equal to natural log of half, which is natural log of negative natural log of 2. So our sum S now becomes natural log of 2 minus Euler-Mascheroni constant. In case you want to write this as an infinite series, so you can have sum from n equals 1 to capital N minus 1 to the n plus 1 over n, that's natural log of 2, just the Taylor series of that, plus natural log of n minus 1 over n in the limit that this capital N goes to infinity. These two last terms are the negative Euler-Mascheroni constant. So that's what this sum evaluates to. Natural log of 2 minus Euler-Mascheroni constant. Isn't that a really nice result? I mean, the Euler-Mascheroni just comes up again by virtue of this digamma over here. And I'm really glad that I proved this. Otherwise, you guys would have just been like, what the hell is going on? So I think let's end this video here now. I hope you enjoyed it. So please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe, keep doing math. Please stay tuned for more content. And peace out, signing off.